The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Let's get started. So today I am going to talk a little bit more about performance issues in parallelization. A little bit move out of the Silk world to what people are doing otherwise. So normally what we have done so far is we looked at Silk. It provides a very robust environment for parallelization. It hides many issues and eliminates many of the problems out there that if you find other ways of parallelization that you have to deal with. And in last lectures, we looked at things like cache oblivious algorithms, algorithmic issues like looking at work and span, and in fact, in your projects, you're going to use all these nice concepts to get you nice parallel running code. But if you look at a lot of these codes, as well as the way people normally parallelize code outside probably Silk, and there are a lot of other issues that arise, things like synchronization issues and memory issues. Today we are going to, I think, focus mostly on memory issues, and we are going to use OpenMP instead of Silk. And most of these issues will be affected on Silk sometimes too, but Silk tries to hide them from you. There's a layer of abstraction. It's hard to kind of get to those issues in there. So we are going to look at this thing called OpenMP. So today we are going to address things like granularity of parallelism. There are so many things, it just went out of the page, I guess. True sharing, false sharing, load balancing issues that you have to deal with. So Professor Lysenson keep talking about that we want to be out of all this, not dealing with voodoo parameters. Today, we are actually dealing with mainly with voodoo. So I guess this should be the basically Halloween lecture. So we are all about voodoo today and see how we can deal with voodoo issues. So if you look at a Silk program, here's a nice simple matrix multiply. Seems to be our canonical example these days. What you can do is you can put a Silk for in these two loops and get a nice parallel performance. However, which iterations run where, how the memory is arranged is up to the Silk scheduler. Silk scheduler is doing some work stealing. Depending on how the work gets distributed, the process will get work, it will happen, hopefully everything will go nicely. And so what that means is it hides the distribution and load balancing issues. So it's nice if you have access to Silk, but many other contexts you might not be, and even within Silk, some of these issues might show up. So what we are going to do is like step one below the Silk scheduler. So there's this system called OpenMP. It's a more simplified model of parallelism. So what it tries to do is, instead of giving this very thick runtime system, it lets you basically direct access to the processors. So what that means is there's normally what we call a fork join model. It's similar to Silk basically, that when you do, we can do fork into different workers and join, and more or less you can actually bind these workers to threads sometimes, or make sure that the number, I'll give you some techniques how to do that as I go on. So for parallel loops, you can do data parallelism differently, and parallel section you do something like fork join, and you can select bunch of static or dynamic scheduling policies. So for example, in OpenMP you can say for this loop that add a pragma to in front of this loop and say this is OpenMP parallel loop in here, parallel for loop in this one, and schedule it using static chunk. I will tell you what exactly that means. And that gives you direct access to where, how each of these parts would be run. So let me get a little bit into detail. So assume you have four cores in there, four processors. So now in OpenMP, you are basically opening the entire world underneath, and you have to kind of see what's going on. And if you say schedule static chunks of 4, assume you have 16 iterations. Here's my 16 iterations in here. So each of these dots represent a value for I. So what it says is you take chunks of 4 and basically send across it. So what happens is first 4 iterations will go to core 0, next 4 will go to core 1, core 2, and core 3. So you know exactly which iterations run where. So this is a very static thing. You have full control of what's going on, whereas in Silk, it's up to the scheduler. So the nice thing here is you have full control, but you get enough rope to ham yourself if you do things wrong. So this is a double-edged sword in that sense. So instead of doing static 4, if you do static 2, you're assigning chunks of size 2. What it will do is it will assign chunks of size 2 to the 4 cores, and then you're not done it, and then you start with again core 0 and assign chunks of size 2. This was called a block cyclic schedule. And if you do chunk of size 1, it's called a cyclic schedule. You go cycles, just assigning iterations to cores. Okay, so far so good? Okay. So I want to do something. So I have this program. This is again your run-of-the-mill matrix multiply. And I ran a sequential single machine, and I got this performance. Then I said, look, I want to parallelize the outer loop. So I parallelize this loop. What should I get? Run fast or slow? I want to just check whether you are awake or sleep. How many people think it will run slower? It's not a trick question. This is just to make sure that you actually participate. How many people think it's run faster? Okay, good. That's, what do the others think? Okay, they're probably in there checking their email or something. Okay, but so yeah, actually it ran faster. This was not run on the current cloud machines. This was a previous generation machine that I ran, so it ran about 7 times faster. So this was great. I parallelize outer loop. What happens if I parallelize inner loop? So this says this I loop runs parallel. Here I run the J loop in parallel. How many people think this runs faster compared to this one? How many people think it runs slower? Okay, there's some consistent answer here. Why do you think it will run slower? So okay, it runs slower, so actually we'll prove that in there. It's a little bit slow. Why is it slow? Exactly. So what it's doing is it's basically spawning many times in here, because every time you have parallelism, you chunkify and give the processor. Here you are giving a lot more smaller chunks inside. So let's look at how this is basically run. So normally you can think about an OpenMP program as you have one sequential thread. You run the main program. And then assume you have n cores, you might have n-1 other threads just waiting, okay, for work. And then when you come to a parallel loop, it says, okay, set up what you want to run on other basically cores and release these waiting people and let them start working on the parallel work, and also I will start doing my own chunk. So suddenly when you say parallel 4, it releases all the other cores to go and run that part of the code. And once it's done, it will say, okay, I'm done. And it will say, I'm done. I have to wait till everybody is done. So even if the main guy is done, it has to wait until everybody is finished, and then start executing the sequential part again. So this is the gist of how OpenMP program will run. And if you realize, there are overheads here, because you have to basically make sure all these guys are woken up. So there's some things has to be issued. And there's a delay between these guys can start if everybody has equal work. This might not finish on time, because it might take some time for this to start. And then at the end, it has to also tell this back, again, I am done. So there's a lot of synchronization going on, locks and unlocks. Here it's called barrier synchronization. This is called a barrier synchronization here. And so if this work is small, this synchronization starts dominating. So what happens is if you have what we call fine-grained parallelism, too little work in the parallel region, and synchronization basically start dominating your time. So how do we detect this? And sometimes when you run something parallel, it might even run slow, because the amount of stuff in the parallel region is so small, all the overheads start dominating, and that's not a good way. And also, sometimes you assume when you keep increasing the number of cores, you keep hopefully you want to see nice parallelism increase, but it doesn't. Even though you have enough iterations, but that means you're running a lot of small chunks, even though you seem to have a lot of parallelism available. And also you can measure the execution in the time in the parallel region. If parallel regions are run very short time, this happens. We saw this effect when we are doing silk. Remember? When did we see this granularity effect in silk, and what did it do? When you write silk programs, divide and conquer programs, where did the granularity start showing up on us? May not be exactly this because the scheduling is complicated. Okay, answer.
2 by 2 matrix.
Yeah, something like 2 by, like for example, that's the reason we wanted to have a large base case. Because if you didn't put a large base case, start dividing into small and problems, and if the schedule is smart, it won't be doing exactly this, but it's always good to have these large granularity chunks at the bottom. So how to get coarse granularity parallelism? What we need to do is reduce the number of parallel invocations. So you want to always try to look for outermost loop you can get, or the very large independent region. So you go look, and not the innermost thing you want to parallelize, you go up, until a point you can parallelize, and that's the best way to get good performance. Okay? So if you really compare these 3 programs here, again, what you see is, of course, this has no synchronization. This has n amount of synchronizations. Here, n squared synchronization. There's obviously a lot more synchronization going on, and that is where this cost comes from. Okay, so now I'm switching a little bit in here. I want you guys to look at this program a little bit. So what am I doing here? I have a 2D loop nest, and I am just basically adding matrix P to matrix A. Okay? And then I have another loop test here, adding matrix C to matrix A, and what am I doing in here? I am basically going through matrix A in the other direction in here. It's not really a transpose. I'm not transposing. What I'm doing is I'm actually doing a mirror, because C gets mirrored on I-axis, because you go the I-axis the other direction. Okay? So it's not really a transpose. So I do a mirror addition in here. Okay? And then I'm asking for the 2 outermost loops to be parallel. So if you run this sequential, okay, you get about 30 seconds, 30 milliseconds, I guess, in here, to run in here. So that is in the, but if you run it parallel, what do you get? Should you run faster or slower? Okay, I guess, anybody want to take a guess? I mean, sometimes some of these questions you might not have enough information to answer, but still good to just take a stand on one direction or other. How many people think it runs faster? How many people think it runs slower? Okay, oops. What happened? What happened in here? Can anybody able to point out why it might be running slower parallelly than running sequentially? Yeah, there's a cache issue. What's the possible cache issue in here? Yeah, that's what happens is, if you think about it, the first iterations of I gets to the first core. I'll have some diagram. I'll show it to you in there. And here, only the last data elements will get for the first iterations because you are going in the other direction. So if you look at a little bit more deeply into what's going on, number of instructions seem to be a little higher. This one I couldn't actually explain why this might be the case in here. If anybody has idea, you can say that. But this was kind of this might be, I don't know, that's cycles. Huh. Anyways, and CPI. Oh no, never mind. Okay, I can explain this. Because this is a sequential run. This is a sum total of a parallel run. So because of all the overhead that happens, because this was running on, I think, 8-core machine. So you are running 8 times of small copies. There's a lot of overhead that goes around, synchronization and stuff like that. So number of instructions just blows up. But for each core, you have to do, you don't have this blow up.
Would that happen in Silk? Because does Silk have different processor affinity things in OpenMP? Because it seems like if the program, if the language.
Good question for Charles. Does Silk look at kind of processor affinity information, or it's no? It's just pure work stealing. Yeah, I mean, if you like to execute it locally, if we have good cache oblivious algorithm, but if there's no cache obliviousness, you might steal something where data might be somewhere else.
But you'll still mimic the cache behavior of the serial code, except for when you steal.
Yeah.
You start again, you should repeat it.
Yeah, so okay, we don't have a mic in here. So what Charles says, it will try, okay, there's Mike, there we go. So, but if you have 2 different these regions, the way the parallelization happens is not, can be different.
Yeah, in Silk, what happens is the code is mimicking, for the most part, exactly what the C or C++ code would be doing. And so you get exactly the same cache hits and misses, except when you steal, it's like starting over with an empty cache. Okay, but as long as you have sufficient parallelism, the steals don't occur very often. And so therefore, you end up getting the same kind of behavior that you would get out of the serial
Yeah, but Charles,
code.
in this one, because you have to steal everything here, the between here and here, the parallelism will be different.
There'll be no affinity between those two.
No affinity will be there.
That's right.
Exactly. So in the sequential one, everything fits in the cache, so there will be affinity because we are not doing parallelism, and that's what I think will happen here, because you had no affinity.
In serial code, there's no affinity. In serial code, there's no affinity.
No, serial code, if this fits in the cache, it's running on 1 core. So if it fits in the 1 core's cache, you are happy.
Yeah, so the issue is, by the time if you only access it once, by the time you fill up the cache,
so if
it takes the time to fill up the cache to get them synchronized, yes.
So if it fits in the 1 core's cache, it's okay. Otherwise, it has no affinity in here. So the key difference in here is, of course, CPI is low. We don't know exactly why, but invalidations. So what you find is there's a huge amount of cache invalidations going on. Okay, so that should give you a feeling what's going on. So let's look at what might happen. So I am showing this machine was run last year on what we had were CAG node machines that were basically core to quad processors. So you had 8 cores in here. And I put you don't have to look at this table, I put it in the slides, you can look at it later. And so this is the last year's machine, and of course this year's machine is different. We have 2 6-core processors in here, so this is what we got 12 cores this year. We have 2, isn't it? 2? Yeah, okay. So right now I'm showing numbers for this one, and later I will show what happened in Halem. So if you look at a cache, so what happened is each of the data items in the cache can be in multiple states. This is called MSI protocol here. What that means is the item might be modified. If it is modified, it can be only in 1 cache. Okay, if anybody else want to touch it, it has to get it out of the modified state. Or it can be sharing. Sharing means it's reading. So that means that item is read by multiple people, and that can have multiple copies. So sharing items can be in multiple places. Okay? However, if you're modifying, you have to invalidate the items in everybody else. So that means if I modify something, it can only be in mine. If other people had that data, I had to go and invalidate it. So if you modify this, I have to go and invalidate it. So there's a sharing state. That means everybody is able to read this. But if I ever want to change that, I have to go and invalidate this one. So what that means is when I start writing, I am invalidating it from everybody. So even though if everybody kept a copy, when I start modifying, I have to get my own copy, and everybody else will invalidate. And then if somebody else want to read, for example, if this guy wants to read X, basically this has to make this a sharing and back to sharing. That means I have to get the value 13 propagated, and this becomes sharing again. Okay, do you get that? What's going on in here in the cache? So reads, everybody can keep a copy if they want. Writes, only one guy can keep a copy. So what happens is true sharing is, so you have these two different cores. So I want to read something. So I get it from outside, probably on main memory, and I put it in my cache in here. And then the next guy wants to read the same thing, write the same thing. Assume I'm writing that. And once I want to write that, I can't keep this copy. I have to invalidate it from here and get a copy here. And then if this I want to write it again, I have to basically invalidate it from here and get a copy. If I'm reading, both of us can keep copy, and this kind of keep bouncing back and forth, back and forth. And so if you bounce too many times, you get all these invalidations. So the fact I looked at that I has invalidations basically tells me something like this is going on. So what's happening in this program is when I parallelize this for loop, my for cores, basically since I'm doing Aij, is going to get this nice distribution of data into the caches. Assume it fits in cache. Okay, so all this data nicely fit into cache, and now I'm pretty happy when I run this one because I got this data into the cache and I write it. But the minute I go in here, basically this data has to kind of like flip around. Okay, because I am going, this is n minus I in here, so this data has to flip around. And by doing this, basically what I incurred is huge amount of invalidations, and that slowed down. Okay, so that's why it didn't work well. So what can we do? So this is basically when you have these read write and write write conflicts in here, and you have to actually move the data across in here, and what you can do is look for this true sharing. You can look at the invalidations and see how much, if we have excessive invalidations, we have a problem. And how do you eliminate that? You want to make the sharing minimal. If you want to get some data into a cache, you want to try to keep it there as much as possible. And if you're using, you want to try to align everything across. So even across different regions, it will use the same kind of things. Or enforce some kind of affinity technique to keep the data alive. So there are a lot of techniques in there, but true sharing can be an interesting problem. So in here, simple change is you basically, instead of changing A, you change C. So you ran A the same way, but now what I have done is now I am doing the mirror by changing the access to C instead of accessing to A as the same as this access. So these two are the same thing, and the minute I do that, voila, I get good speed up. Because if you look at that, my invalidations has gone down, my L1 cache miss has now really gone down, I'm not doing anything. And of course I am doing more instructions here than this one, because I think the difference between instruction here and here is because a lot of times synchronization operations are dynamic, because in a wait is counted as instructions. You are waiting, busy waiting in there. So this number is not a really constant number. And okay, question.
So not a question. So another thing one could do here is do loop fusion.
Yes. Here is a nice way of like putting both of the loops into one and do loop fusion. And that works. If in this case, you can do that.
Yeah, so loop fusion is where you take two loops and you convert it into one loop. So in this case, you could have just written, one nest, which has two things going on inside, and then you would save all the loop overhead and the scheduling overhead So rather than doing it twice, you actually have reduced the overhead to just the parallelism of the one loop. Okay, so if you look at that, you'll realize that you could somehow make it just be a single nest with two statements in there rather than one.
So basically, instead of just get rid of this entire thing and move plus C into here, basically. And I could have just done it in one loop nest. That's what loop fusion would do here. So we can actually even do much nicer in here. So but just for example purposes, so now I really reduced this one and got that. So this is great. CAG nodes really showed this classic problem in computer architecture. So I'm like, OK, now we have new machines. Let's try it and see what happens. What does this show? This is your nice cloud machines you got now. I have no slowdown. I was really disappointed. Because beforehand, I had this fault sharing going on in here and had a really big slowdown. But this one, in fact, the difference is very small. And when you look at any kind of performance counters, they are pretty comparable. There's nothing much going on here. So what do you think is going on in this new architecture now? Why this might be? That's an interesting observation, but also we have, yes, core 7 basically is 2 by 2 in a die, but we also have 2 different processors. So that's there too. So in some sense, when you get our 2L processor, it's just 6 by 6 and 6. So that's there. That might help. That's an interesting observation. What else might be going on here? Why do you think they managed to get this one? What might be other answer? What can hide these kind of delays? That can happen, load delays and cache misses and stuff like that. What techniques in hardware can hide those? Just not the speculation. Prefetching. So what most hardware has an internal mechanism, when you start fetching data, you say, aha, I see a pattern. I know you want to get this thing. Let me go forward and bring more data, thinking that you are going to follow that pattern. Okay, most of the superscalers for, I think, around even a Pentium had some simple prefetching going on. But most of the time, what happens is the prefetch engine can't keep up. If you are getting there, it's prefetching a little bit further, you're going to catch up and you're going to stall because you have more misses in here. I think basic NLM has a really, really good prefetcher. And we saw it in our architecture slides too, that a lot of things that used to happen before is gone. So this is really good. What that means is a lot of weird stuff that's going on, the architects are making them disappear. So these kind of problems doesn't show up. So that's a nice story. The other part is, OK, now if you start really tweaking your program to one architecture, you wait a generation, and then now we have done either the tweaking, if in the best case, tweaking has no impact, and it's not affecting anything. In most of the time, worst case, tweaking actually slows down the program because now you are trying to do something complicated that's just not needed anymore. So even though this kind of thing showed up in the NLM architecture, it's not an issue. But if you go to many other small architectures that don't have that much very powerful prefetchers, these kind of issues you will see. So for example, if you go to a cell phone architecture, Atom, you will probably see these kind of issues happening. Any questions here so far? So it's good news is you guys don't have to worry about it too much, but at least it's good to know the technique because you will see it in other architectures. So now I want to switch a little bit into looking at programs that doesn't have what we call data parallelism. That means you can start and say, oh, embarrassingly parallel. So everybody get a different chunk and run. And we are going to do a little bit more deeper into, say, looking at programs that are a little bit different. So I want to come up with this little bit of representation to represent the program. And so if you think about iteration space, Actually, before I go down to dependence, I want to also do a little bit of load balance. So here's a loop that in my iterations, the first one I runs from 0 to 8, but j only runs from 1 to 8. So each I have less and less amount of j iterations, basically. Okay? It's a triangular loop. Okay? And so, okay, so this is the way to represent iteration space. So I want to represent data and get back to this again. So if you look at a data space, you can assume data, iteration space could be this funky triangular hyperplane type things. Whereas data is not, data is mostly rectangle linear, multi-dimensional rectangle. So for example, if I have A10, it's a one-dimensional one. This is basically two-dimensional data, and you can three-dimensional cubes and stuff like that. You can represent data like that. So this is a way to nicely represent, and when you start thinking about it, so you can look at what's going on. Okay? So now you have this loop again. So here's the basic iterations. And here's the data. Assume this is both A and B. There will be another one matrix like B. What data each iteration is going to touch. So these are the data that it gets touched, and here's iterations you are going to run. So we can say OpenMP parallel 4. So what happens when you do parallel 4? So I'm going to get parallel, and so one core get this, another core, another core, another core, get these iterations running. So what happens if you do this one? Do you get really good performance? Why? It's not balanced. The load is not balanced in here. So basically, if you run sequential and if you run block distribution, I get about 3x performance in here. So if I look at closely, here's the number of iterations given to each core. The first core gets almost nothing, and the last guy gets a lot of work. Here's where something like the Silk runtime can come into play, because the Silk runtime, basically, this guy will finish this and start stealing from somebody else, and so it will be done nicely. But whereas if you do a static schedule, you are in this big bind. You don't have too many things going on. So, and basically, this is what we call load imbalance. So what you can do is figure out a complicated partitioning, so you can get statically partition this out, or you can do something like the dynamic schedule, like the work stealing scheduler. That's a possible solution. So how do you detect load imbalance? Basically, what you might want to do is, for each of the different sections you are running, you want to look at the time it takes. And in the min and the max is very huge varying. That means there's a load imbalance going on. So you might want to check and measure each of the parallel regions time is taking. And that gives you this field. How to eliminate load imbalance? So you either use a dynamic scheduler that will deal with that, or you can do a different distribution statically that will not partition in these large blocks. So let me show you a static part, because we have already learned the dynamic part before. So now instead of doing that, we do a cyclic distribution, which is static 1. That means if we have a lot more than, then it will be a little bit better distributed. So what happens is the processor 0 gets this one and this one, 1 gets this one and this one, so on and so forth. So there will be a little bit of an imbalance in there, but if you have enough of cyclic, the imbalance would be much lower. So should we run faster? So here's the basically kind of iterations each guys get in here, because this looks very balanced, because I had a lot more iterations than this 8 one. This is not that balanced still, because this guy get a lot more than the first one. First one get 6, and the last one get a lot more. But what do you think is happening here now? I ran again slower. See, I guess the people in class last year had things so worse because they had this old processor that did all these crazy things on them. And you guys got the fast one that doesn't do that. So why do you think cyclic distribution is running a lot slower? What might be going on? Spawning overhead is not that much because you don't run this and synchronize. What you do is you run the same amount of threads and say now instead of running continuously, you run jumping over iterations. You say run 0 and 9, whatever, jump over iterations. What do you think? Okay. Yeah, there's a cache issue. All those time when the question is not sure, it's probably a cache issue. What type of cache issue do you think is going on? Yeah, I can't hear completely, but let's assume, let me show you what happens. So you got off well. Okay, so if you look at the details here, so let's look at happen. So this is running obviously slower. It's trying a lot more instructions, but instruction doesn't tell you too much because a lot of them might be synchronization cost in here. So instruction is not that illuminating here. The big illumination here is this one again, invalidations. I have huge amount of invalidations going on. So here is a case of fault sharing. So what happens is now things next to each other, we were given to multiple different processes. We're not touching the same data. Everybody is looking at somebody else's data. But, so what happens is assume I want to write this data item. I write that data item, but I get the entire cache line. Okay, because when I ask for that, I get my synchronization by the cache line. I get this entire cache line coming in here into this one. And the next guy say, wait a minute, this guy want to write this data because now instead of blocks, I basically gave each strips. Basically, there's a lot of overlap between strips. So this guy says, and in order to write this one, I have to get the entire cache line going back here. And so if you want to write that again, I have to get the entire cache line going back. Even though we are writing different data, because we are sharing cache lines in here, this thing keeps bouncing back and forth, back and forth, back and forth. I have a lot of cache misses. Things are really slow. Okay? And so what happens here is if you look at the cache lines, where's my animation? So cache lines, basically there's this overlap. You can't see that very carefully. What happens is between these lines, there will be some overlap of cache lines. Okay? And this overlapping cache lines keeps bouncing back and forth in here. And so what happens is basically cache line is bigger than the data size, or there's overlap in here, and cache line is shared when the data is not shared. And so how do you take fault sharing? Again, too many conflicts. You see, you assume there's the nice parallelism, but suddenly you don't have speed up, and you have a lot of conflicts here, even though there's not supposed to be any sharing. And how to eliminate fault sharing? Make data used by each core contiguous in memory. That's a good way of doing that. Or paired at the end. So these kind of, at the corners, there's not going to be any overlapping here. So in here, one thing you can do is, you can measure each thing that each of the cores get, we can make contiguous. But beforehand, what happens was, a core used to get this line and this line. They are different places in memory. But you can make these two contiguous in memory by basically now instead of having a two-dimensional array, you made the array three-dimensional, all these arrays. So what used to happen was each of them were going to get this line and this line, each core, or all these lines that were in different parts of the memory. In here, each got only 2 lines, but they are different places. So if you are more cyclic, you will get a lot more lines all lower memory. So what we can do is, can we arrange the cache? So if you think about this, you can think the cache, now the data, as instead of 2 dimensions, as a 3-dimensional data. 1 dimension is these cyclic parts in here. So you can do that. And then you can change in a way that the cyclic part, the one that I got this line and this line, now become contiguous. So kind of, you think about data as instead of 2 dimension, think about it as a cube, and you kind of change the cube for the inner dimension to be the one that's contiguous. So you can do kind of data munging and data transformations and get there. Okay. So now what happens is the row core 0 gets just contiguous things in memory. and co1 get contiguous in its memory. So if you try to make it contiguous, that's great. So between padding and making things contiguous, you can get good performance. And if you do data transformation, voila, my invalidations just went down drastically. I again have a nice load balance in here. Invalidation went down drastically. That means my CPI increased a little bit, and I get really nice speed up. Okay? So here are the kind of crazy things you have to do if you are doing things like algorithms that are not cache oblivious, and if you are doing directly parallelizing yourself without having a nice runtime to help you, something like a sync runtime system. So I'm just going to summarize these because these are important. We looked at a bunch of cache issues. We looked at cost misses, capacity misses, and conflict misses before. And today, here are some examples of true sharing misses, where what happened was I am actually really using data, but I set up my parallelism in such a way that between different executions, my data has to move across. Even with this agent. So I am actually truly sharing data, but the data has to go to somebody else's cache. So I got a lot of invalidations here. More insidious one is more like fault sharing, where you assume there's no sharing, nice parallelism, everything, except the program run very slow, and that can be because of fault sharing. So we just kind of touch on these two topics. Okay. So let me switch gears a little bit about dependencies. We touch on the dependencies a little bit, and this is to find programs that are not completely parallel. So normally what happens is a true dependence means that I'm writing and reading value, and anti is the other way around. And if two guys are both writing, the order has to maintain, that's output dependence. And data dependence in a loop, because these are single items. So if you have array, this is becomes a lot more complicated, because there's no simple thing in here, because it's not just using the same iteration. You might be using data from different iterations. So what happens is there's a dynamic instance of iterations. So one iteration writes the data, and somebody else might be reading the data. And that is basically what the order we have to capture. Let me give you an example to kind of demonstrate what's going on. Okay? And when you have arrays and loops, this is why the things are very complicated. So in order to give you an example, let me look at this program. I have a simple program here, AI equals AI plus 1. My iterations, I'm running 5 iterations in here, so this is my iteration space. I have a large array, so this is my data space. Okay? And now I keep running this program. So what happens is this is time going down in here. So the first iteration, basically I first read and then write. Then the second iteration, I read and write. Third iteration, read and write. Fourth iteration, read and write. Do you see how this is going on? This is the first iteration, second iteration, third iteration, fourth iteration, whatever. Okay, so what happens is first iteration, read this value, A0, and write the value A0 when you're writing. Second iteration, A1, A1, A2, A2, A3, A3. So now, when this is writing, okay, there's a dependence between these two. Is it a true or anti or output dependence between these two? What type of dependence do I have? So here's my dependence. But true dependence is what? What to what? What's the first thing that occurs? What's the next thing that occurs? Anybody want to answer? If you, write to read. So you have your first thing has to be write to read. What's this? This is a read to write. So what type of dependence is this? This is anti-dependent. So here's anti-dependence in here. But the nice thing about that is this dependence didn't cross the iteration boundary. So these black lines are my iteration boundary. So this is first iteration, second iteration. So there's no iteration crossing in here. You can kind of depict it using each of these is my iterations, and my dependence is within the iteration, same iteration. So same iteration, I have dependence in here. Okay? This is a simple case. So let's look at something a little bit more complicated. So I have a AI plus 1 equals AI plus 1. So what happens is first I am reading AI, and then I am writing AI plus 1. I am writing AI plus 1 in the same iteration. Next iteration, I am reading now AI. Now this is A is 0 and 1. This is A is 1. I am doing that. I am writing AI plus 1. I am writing 2. Okay. So I have a dependence like this now. What type of dependence is this? This is a true dependence because I am writing and this is actually reading what's this writing. So is this loop parallel? No, because what happens is if you look at that, each iteration depends on the previous iteration. So you have to actually have this dependence going back and forth in here. Okay? So let's look at a couple more other things. So here's AI equals AI plus 2. So I am basically reading AI plus 2. So I am reading this one, I am writing this one. Reading this one, writing this one in here. Here's my dependencies in here. Is it a true or anti in here? This is anti-dependence because I am going from a reading to a write in here. Can this loop be parallel? Can this loop run parallel? So can every iteration run parallel? Okay, of course, there could be ways to parallel. No, because what happens is if you look at that, there's a dependence that goes like this. And of course, there are 2 chains, so you might, if you are interested, you can run at least 2-way parallelism. You can run 1 chain parallel to other chain, but you don't get that much parallelism. How about this one? 2i and 2i plus 1, there has to be I here. Is there any dependence in here? Nope, because one is you are reading odd elements and writing even elements, so there cannot be any dependence, so you can have run this in parallel. Okay? So this is the kind of interesting thing that's going on. So next, I want to look at something a little bit more complicated. So let's look at this. So here's a classic algorithm called successive over relaxation. So it kind of simulates a lot of time things like heat flow through a plane. So the idea there is, so let me illustrate what it does. So assume you have a big metal sheet and you put some kind of heat source in one place, and after some time it all reaches steady state because the other side might be cold, and you want to know each part of the sheet what's the temperature. Okay, because temperature can leak out, and there are just more things like you have a heat source, and the other part you put it into a glass of water or some kind of a sink. So what is the heat distribution? So one way to compute that is basically saying, okay, look, the heat value here is basically the average around all these other values right now. Okay, because if something is too hot, the heat is going to propagate. Something is too cold, the heat is going to propagate. So it kind of has to be average around that. And then you take the average in here. So what it's doing is calculating the average in here. And then you have to do it many, many times. So if you have heat source, at that point it will be very hot, and then it will start propagating slowly and kind of propagate down. And the cold side in there, so after running many times, it basically stabilizes. And at that point, you have the kind of heat distribution that it would have. This is the kind of calculation you do. So this is the calculation. So what you're doing is calculate this. You are reading this, and this, and this one, and updating that. And then you do it for t timestamps. So you're just going around doing each of these things first and doing it for t timestamps. Okay? So we won't like to run this parallel. So here, let's look at, so here's my basically data space. Here's my data items. So here's my array, 2-dimensional array. So this is how I'm trying to update. I'm reading all these 5. So here's my iteration space. So what I have looked at is I don't want to, it's hard to give you a 3D diagram. I don't have a 3D projector. So what I'm showing here is t dimension here. So this is the previous iteration, first iteration. So first you go Tij. So you go through t, and then you go through I in here. And then when you're done, you go to this iteration, and you go this one. So here's how you iterate. So you run this one, 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 and then go increase t by 1 and go like this. And right now we are here. We are trying to update this one. Okay, this is what we are trying to do. Okay? And that means we have already finished up to this point. All these points are finished up. Now what we have to do is figure out when I am reading who actually wrote this value. Okay? First of all, let's figure out which iterations might be able to write this value. So if you look at this value, the relationship in between here, this one basically is ij, and this is ij, ij, ij. These 3 iterations can write this one. So and these iterations can write this one. Let me go to this one. So what? Okay, this is a pretty darn complicated tree. So what that means is this in this one already wrote something. This is what I'm reading in here. This one already wrote something. This is what I'm reading here. This iteration wrote something. I read it here. Okay, everybody following so far? How about these guys? Who wrote the value I am reading in here, these iterations? Because in this one I haven't reached there yet. So who has to write that? So we assume this is t equals 1. So which t equals, so somebody here has to write those things. So what that means is these also wrote all those values because I have done these iterations. But the interesting thing is some of these values got overwritten because this value got overwritten, this value got overwritten. So these 2 values disappear. Because this value got overwritten by this guy, this value got overwritten by this guy. Okay, but we haven't overwritten this value, and this value yet. This one basically I am just updating, but I have to first read this one. Do you see this? Everybody following me? Okay.
I got lost.
Okay.
What are your thinking about?
So what happens is I am trying to update in this iteration because this array gets updated multiple times. But in each iteration you are only doing one update. So I am trying to read and write in here. So I need to read all these 5 elements in this iteration. So I want to figure out who wrote that. Okay. This one can be written by this guy and this iteration because this iteration writes its value in here. Okay? In some sense, this iteration right because this is it's writing ij. I mean, my diagram is not that great because I have 3 in here and 5 in here. So just bear with me on that. So I assume I'm writing ij in here. So my iterations go from 1 to n, but my data goes from 0 to n plus 1 basically. 1 to n minus 1 iterations, 0 to n plus 1 data. So the data is bigger than the iteration space because of the n around. So what happens is when I'm in this iteration, we will say this is 1, 2, 1, 2 iteration. Okay, I will write this value. Excuse me. This iteration will also write this value. Okay, you see that? Because all these this iteration will also write this value. But right now, who's the last guy who wrote it? The last guy who wrote it is this guy. Okay, because this iteration wrote it and after that it got overwritten in this one. But this one haven't occurred yet, so it haven't been overwritten by this guy. So the last guy who wrote it was this one. Okay, so that's why I had to eliminate this. But this data value, I haven't executed this iteration yet. So nobody had written this one in this time step. So it has to be from the previous time step. So I read 3 values from, 2 values from the current time step, 3 values from the previous time step. These 3 values have to come from the previous time step. These 2 values have come from the current time step. You see that? Okay, good. So what that means is, because dependence means, okay, this line, this dark black line saying, I am reading a value in current iteration that was written by this iteration. So that means I have to have a dependence between these 2 iterations. Okay, this line, this dark black line saying, I am reading a value written by this iteration, so I have a dependence in here. This line means I have a dependence between this iteration to the current one. This line means I have dependence between this iteration to current one. This line means I have dependence between this iteration to current one. Do you see that? Okay, so now I want to see how I can parallelize this loop. So what can I do? So I look at all these dependencies. So this is at this point, I don't have to think about all these, where, who wrote what. I can say this is dependence. In order to, what this means is, in order to do this iteration, all these iterations has to be done, because I am using the values produced by them. So these has to be finished before I can touch that. So the parallelism means I try to do things in parallel. So can we parallelize this loop? Can you run each time step separately? No, because I am using these 3 values from the previous time step. So I can't run this time step t equals 1 until t equals 0 is done, or t equals 2 until t equals 1 is done. Okay? So I can't parallelize this loop. Okay? Can I parallelize this loop? Why? Which dependence stopped me from parallelizing this one? So I'm looking at I. This is my I dimension. Which lines? How many lines at least tell me? How many dependencies is going to stop me from doing that? So, okay, good. I have controversy. Somebody says 3. Somebody says 1. Okay, let's get a vote. How many people think it's 3? Okay, there's 1 vote for 3. How many people think it's 3? How many people think it's 1? Wait a minute. 1 vote, 2 votes for 3 and 2 votes for 1? Okay, where's the rest? For 2, for 0, can't be 0. If it is 0, it's parallel. Okay, we assume it's not parallelizable. Okay, so what happens in here? The right answer is actually 1, this one. Because these things doesn't participate because these happen, this has already happened. When you go to ij iterations, t is already done. So you're going from t. So you're looking at the current t iterations because you're in the inner loop now, inner 2 loops. So the t is done. So this all already is done when you go try to parallelize I. So I don't have to worry about these 3. In here, because actually I'm using t something here, I am in trouble. So when you go into the, so when you go look at this one, I have this one. Okay? So every dimension, there's a dependence in here. So I can't run it in parallel. So does this mean that there's no parallelism? Who thinks there's no parallelism? Who thinks there is? Oh, somebody thinks there's no parallelism. Who thinks there's parallelism? Okay, there's more people think there's parallelism. Let's see what we can do. Of course, question.
Do you mean that trying to figure out how to word this. Do you really want to have a dependence on the same time step? Squares from the same time step for this calculation?
Yeah, I mean, you can do, this is the way this SOR is sitting. So there's a dependence between time step. There's another SOR, what they do kind of a red-black. So when you calculate the next time step, you calculate it right and completely new array. So there's no dependence. So that's a different algorithm. Okay, this algorithm basically uses some value from all, because the value, the algorithm you're talking, you have to create another copy. So you have to have 2 copies. You're bouncing back and forth. Nice, no problem in here. But then you have to have twice the amount of storage. Here you are updating in. And since this is kind of running up enough iterations to kind of until it converges, doesn't matter. It doesn't seem to matter that the scientists has figured out it can doable. Like, okay, so we cannot find a loop, what we call do-all loop to run. The do-all loop means there's no loop carry dependencies. It's fully parallel. This is the best case. So what happens is when you get there, you can start everybody can run in parallel, and when you're done, you can stop and then do that. So this is the do-all loop. Of course, there's no do-all loop. We can look at every dimension, we had some kind of dependence. So there's another choice, what we call a do-across loop. What that means is we have some loop carry dependence. There's something I have to use from the previous iteration. But it's only one thing. I have a lot of other things I can run around that. Only I just have to wait one thing. When it's done, I can just keep running. And if I calculate and send this one early, then I can do my other calculations later. This is not that great. If you look at the dependently here, this definitely has very little overhead in here. This is kind of can be run slow. And of course, this thing gets produced very late. It's almost sequential. So I hope is you can just, the other guy wants something, I can immediately set it very early, and then I can run there. So that's, you can get some kind of do across parallelism in here. So if you want to do this one, this is a little bit crazy in here, what you have to do it in here. And so what first you have to do is you have to say, okay, look, I'm running this loop, the I loop in parallel. But I have to exchange some data. By every time before I want to run this one, I have to basically get the previous I value produced, and when it's done, I can say the next guy can use it. So this is a very complicated one. I don't want you to understand it too well. So the reason I put it to show that, like, okay, if you want to spend a week trying to kind of really code this up and understand and make sure that it works all cases, you can do things like that. Okay? Aha. So this is the true voodoo-ness. Okay.
So in Silk, if you do this with divide and conquer, you can make it be what I called in the tableau construction. Each layer here is basically constructing a tableau. And so if you do it with divide and conquer, you can do it with a very simple recursive code. But you can also do it with a loop that goes diagonally.
Yes, I'm going to get that. That's next. So,
oops, sorry.
So that's okay. So the reason that I'm showing that is because this class is not just about how to make the course exactly run faster. Think about algorithmic issues and stuff like that. So sometimes when you look at a problem, it looks like crazy, and there might be some changes you can do that you can get run things in parallel. So I'm actually doing not diagonal, I actually do something very simple. So what I have done here is I have all these dependencies in here. Okay, so the problem here is when I can't find a single cut that basically has no crossing. But if you look at this cut, a diagonal here, what you see is, in fact, there's nothing that crosses the diagonal. Okay, so this one basically doesn't depend on this one or this one. It only depends on previous one. So I can run everything in the diagonal parallel in here in this one. So of course I can't write anything do all in here, but there's a cute trick you can do. What you can do is you can take iteration space and skew it. Okay, so what I have done is now instead of same thing, instead of this being a square, now I skewed it a little bit. Okay, so what that means is when I'm running first I basically don't run any j, then I run this one and this iteration. So what I have done is I have kind of moved my iteration space around. Do you see how this might be? So now the interesting thing is when I skew, if I look at this line, okay, oops, I can parallelize in this one because all the dependencies come from the previous iteration. Am I right? What did I get? Yeah, I skewed it, and yes, everything in here, these ones are parallel. Okay, and any dependence come from the previous iteration. Okay, there's no current iteration in here. Everything in this one is parallel, so I can parallelize this. So this one doesn't depend on this one or this one. So this is all parallel. Okay, this is a little bit complicated. So if you are interested, go deep. Just go stare at the slides. I have the slides out there to understand how that happens. So if you think about what I'm running here in parallel is the one basically in this diagonal in here. So what happens is if you run this, and this parallel, there's no I don't need this one or this one to run this one. So I can run these, all these diagonal in parallel. But the trouble with just a diagonal is I don't have a place in here to say we unidentified diagonal. So I basically skewed it in and made a diagonal one loop. So then now what happens is basically J loop I can run parallel. This one. So I can do it for all. Okay? So here's something you found problem that has no nice parallelism, but you realize there's kind of what we call a wave front going on here. Wave going on here. So some, not the given dimension, but there was another dimension that you can parallel, so you kind of skewed your space to get that nicely aligned, and you run parallel. So that's all I have for today.